Hello, everyone. We are back to pick up our discussion of training versus testing, understanding this bias variance trade-off, and the general set of trade-offs we face when we're looking at the opportunity to reduce our out-of-sample error potentially at the expense of our in-sample error, whereby we maybe don't want to fit the model that well in sample, where we are able to make better predictions out of sample and reducing that generalization error, that machine learning generalization error term that we talked about before. In this segment, we're going to talk about this problem known as overfitting and a solution to that problem known as regularization. There's actually a pretty quick tweak to the pseudo-inverse estimator for regression models that can incorporate regularization. So we had wrapped up last class by looking at a simulation. I think this is one you may have had to do in your problem set, where we looked at this data generating process that was a sinusoidal function, this sine curve. And we looked at two hypotheses. We looked at a simple hypothesis, just fitting a constant straight line to the data after we had resampled over and over and over again, and constructed the best linear hypotheses in both cases, one using just a constant model on the left here, one using a model where we fit both a slope and an intercept term. And we saw that even though H1 was a little bit more complex, H0 actually provided us with a lower out of sample error. The sum of the bias and the variance was lower under H0. Note that under H1, the bias is lower. Okay, because H1 is a little bit more complex, we're able to reduce that bias, that misspecification error. But unfortunately, it comes at a greater expense to variance, resulting from the increased model complexity. So what we're going to look at next is something called the learning curves, which shows us essentially how the errors change as we change the size of the data set. Okay, so on the horizontal axis here, we're measuring the number of observations in the data set, and we're going to compare here both a simple model's performance, which again doesn't have as many parameters to fit as a more complicated model. And we can almost see right away here that the simple model is going to give us generally a higher level of expected error compared to the complex model. A complex model is going to give us a lower expected error. However, you'll notice with the complex model that out of sample error starts really, really, really high. Okay, for a very low number of data points. It's hard for a complex model in terms of out of sample error to predict well if you're training it on very few data points. So it starts very high, but as we increase the number of data points, you'll notice that out of sample error does converge towards that expected error as well as the in sample error. And you might be wondering, well, why does the in sample error go up with more data points? Okay, and that's happening in both pictures here, right? In both the simple model and the complex model, we have in-sample error increasing, but at a diminishing rate, it looks like here on average, as we add more data points. And the reason being is if you fix the model complexity, right? If the number of parameters is fixed, and then you add more data points, it's going to be harder for that same level of complexity to fit more data points as the size of the data points increases, as the size of your data set increases for a given level of model complexity. All right, so the simple model here, it's got a lot more bias, but it's got a lot lower variance than the complex model does. And again, there are two ways we could kind of decompose these differences between our in-sample error and out-of-sample error. One is a machine learning perspective, utilizing this term generalization error, which is literally the distance between our in-sample and out-of-sample error, versus the bias variance trade-off, which is kind of the statistician perspective on the out-of-sample error decomposition here. So here are the two perspectives on decomposing Eout. Okay, the machine learning perspective says that the difference between Eout and En is captured by this term called the generalization error. So that is this region highlighted in pink in between En and Eout. And the statistical perspective is instead, so the machine learning perspective on the left here in this left diagram, what that is doing is it's decomposing Eout by saying it's the sum of the in-sample error plus omega, that generalization error, right? And the goal was, well, as long as we can make that generalization error smaller, Eout will approach En, and we will be better at learning. We're better at predicting out of sample rather than memorizing and fitting that data well in sample. Okay, so it may be good for us that we can see here by increasing the number of data points, right? It might make En a little bit higher for a given model complexity, but that will reduce the generalization error. Okay, the other perspective on this was the statistical perspective, where we had looked at essentially the same set of learning curves here, but rather than decomposing the out-of-sample error into the in-sample error plus that generalization bound, we saw that we could decompose the out-of-sample error by taking expectations with respect to really the data set itself, treating each data set as a randomly generated variable in some sense. And in doing that, the statistical perspective says that we can decompose that out-of-sample error into these two terms, the bias, or sometimes referred to as the bias squared, plus the variance. Now, a few important lessons from this analysis, from understanding how we're decomposing the out-of-sample error into these two sources under these two perspectives. Either the out-of-sample error is the generalization error plus the in-sample error, or it's the bias plus the variance. Okay, a few important lessons here. First one is that you want to choose your model complexity not based off of what you think the complexity of the data generating process is, but you want to base it off of the complexity of the data resources that are available to you. Okay, very important point there. If you don't have a ton of data, okay, you don't want to go right away with a super complex model. Yeah, I would say generally we want to use a methodology kind of rooted in this idea known as parsimony, where we're kind of aiming for as simple as a model as possible, but no simpler, to make reasonable predictions. So it's tempting to start off, again, putting all the bells and whistles on the model, throwing as many regressors as you can on the right-hand side. But you do not want to match the model complexity to the expected target complexity. You don't want to do this. Okay, first and foremost, we don't know what the target complexity actually is. So formulating some prior assumption about that is generally never a good idea here. You're most likely going to wind up with some sort of model misspecification. The other thing that we can see here is that if you increase the model complexity, this is going to tend to remedy the bias, right? So reduce the bias, okay? But there's a trade-off that we face, and that is it may exacerbate or make worse the model variance. Okay? And that's in line with what we saw earlier, that it's always easy to arbitrarily fit the data by adding more features into your model. Okay, so if you wanted to reduce the variance, okay, you can't really do that by making the model more complex. What you can do to reduce the variance, though, as we saw in the learning curves perspective here, is you can get more observations. You can recruit more observations, increase the size of your data set. But keep in mind, doing that will not actually help you remedy bias. It will not help rectify the bias problem. Bias is related to your model not being specified properly. So bias is really a problem potentially with undercomplexity. Variance, on the other hand, is a problem that you face with overcomplexity, but you can remedy variance by recruiting more data, by using more observations. Okay, so if you had a question in an interview and they ask, how do you reduce the model variance? Answer there is get a bigger data set. Okay, but that will not fix bias. Bias is generally a source of model misspecification, which is generally the practitioner's fault. Okay, but variance is really a function of a few things, including your sample error, which is generally random if you are sampling randomly. It is still possible that your sample is not an accurate reflection of the underlying population function, or that data generating process here. So let's go ahead and talk about this problem known as overfitting. And again, this is the temptation to start complex, throw in as many variables as you can on the right-hand side of your model as inputs. and being really good at fitting that data in sample, right? You can drive that in sample error down to 0, as we saw in the first segment, with more complexity. But the problem is fitting the data doesn't mean you're going to fit or predict that data generating process properly. So let's take a look at a few examples here of the overfitting problem. Okay, let's suppose we have a simple target function. Okay, and that target function is here in blue. All right, so this blue line, that is our data generating process. And along this blue line, we have sampled here 5 different data points with a little bit of noise. Okay, what do we mean by noise? Well, you'll notice those data points aren't exactly on the blue line. For example, this one over here looks to be a little bit above the blue line. So there's a little bit of error in that data generating process. We have some function, looks like a quadratic function here that is generating the data as the target function. But there's a little bit of noise in how that function generates the data. And what we're doing here is we're using a much more complex hypothesis, right? We're using a 4th order polynomial here, right? So 4th order polynomial is going to have how many, local extremum? Well, it's got 3 of them. If the polynomial is of order n, then the number of extremum generally is n minus 1. So there's a max here. We got a min here. There's a max here. And note that because we have those 3 different mins and maxes, it allows the function to kind of turn around and fit a wide variety of data. And in fact, if you look at that red function, okay, our fit, okay, that is the model here. That is the model that we've built. Okay, the red function fits the data perfectly. Okay, it fits that data perfectly. We have an in-sample error of 0. However, if you look at how well that model does at predicting the actual data generating process, you'll note that there is a lot of room for improvement. The out-of-sample error is gigantic, in that the out-of-sample error will be measured by kind of looking at the integral, or the area, the difference between the blue function and the red function, okay, when they're making different predictions. So the out-of-sample error here would be identified graphically by this entire orange region, where we are seeing a divergence between the in-sample error, between our target function, our data generating process in blue, and the model fit that we're looking at here in red. So again, the orange region here, that is our measure of out-of-sample error. And you can see the out-of-sample error is definitely not 0. Out-of-sample error is very big here. Okay. So this is really the problem, is we can be very, very good at fitting the data, right? Our fit with those 5 data points is perfect. Okay. Why? Well, we had a flexible enough 4th order polynomial function to fit that data, which is why it was easy to fit that data. But note, we're doing a terrible job at actually predicting the underlying target function, the underlying data generating process, which again is this blue line. That is our data generating process here in the problem. And our model, again, was the red line, right? That was our fit to the data, but it did not do a good job of predicting the underlying data generating process. We're going to look at a couple more examples here. Here is a situation where we have a lower order noisy target function. Okay, so we got 1, 2, 3, 4, 5, 6, 7. Looks like at least an 8th. So here we can see we have a 10th order polynomial actually. And it's noisy, right? Not every one of those data points falls perfectly on that blue DGP function here. So again, that function is our data generating process in this example. That is the target function that we're trying to predict. And what we're going to do here is we're going to look at 2 different hypotheses on this data. So I'm going to take away the data generating process. You're not going to see that blue line. All you will see are the data points. Okay, and we're going to use 2 different fitting functions. We're going to use 2 different models to predict here using the data set. One is a 10th order polynomial, okay, which you'll notice is going to really match the complexity of the target, which we actually know in this simulation that we're looking at here. But the problem is that 10th order polynomial over here in red, okay, that does not do a fantastic job of actually, predicting the blue function here. In fact, with this 10th order fit, right, this red line here, okay, we see that for the 10th order fit, right, the in-sample error is extremely low, right, which we know. More complexity, more orders, higher order polynomial terms, more betas to estimate makes the model more flexible to fit the data. There's still a couple points that we're not fitting perfectly here, so there's some in-sample error on these data points. Okay. But all the other data points, we do a pretty good job of fitting, right? And you'll notice this simpler green hypothesis here. Okay, it is only a second order hypothesis, or it's a second order fit along this green function. And that green function does not fit the data that well in sample compared to what we were seeing with the 10th order fit, right? The in sample fit with the green function is 0.05, but the in sample fit with that red function is 0.034. So the red function does fit the data better. It is more complex. We should expect that to happen. Okay, but what do we really care about in terms of prediction? Well, I'm going to argue what we really care about is our out of sample error here. And you'll notice the out of sample error, when we compare the green and the red functions against the blue one, which is not drawn in that right-hand diagram, the out of sample error for that 10th order, for that very complex polynomial hypothesis, explodes. Okay, it's there at 9, but the out of sample error for our lower order, less complex target is actually much better. All right, so this again is the idea that you might be willing to sacrifice some in-sample error to dramatically reduce your out-of-sample error here. You're willing to sacrifice a little bit of model complexity to really reduce the model variance. Okay, here is one more example where we have a higher order noiseless target. So here is data generated from a 50th order polynomial. It's a polynomial where we, highest power on a term is something to the 50th power. So we have, at least 51 parameters that we're thinking about estimating here in this model. And there's no noise in this situation, right? Every single one of those data points in the left diagram here is exactly on that blue function. And we can see every one of those data points right along that blue target function. So there's no noise in this problem. But we can still see the same thing, even with a noiseless target. If we compare the performance of that super complex 10th order polynomial to that slightly less complex second order polynomial, okay, you can see here that that 10th order polynomial's out of sample performance is just terrible compared to the second order polynomial, despite the fact that in sample, right, the 10th order drops our in-sample error very close to 0, whereas the in-sample error using that green second order fit is a little bit higher in this case. All right, so the point of all this is that we don't want to get overly excited by inducing too much model complexity early on in our model, and we, in some sense, want to restrain ourselves. We want to tie our hands a little bit, put on the brakes to make sure we're not moving too fast in that dimension that is model complexity. So this problem that we're looking at here is called the overfitting problem. Okay, we're overfitting the data, but we're not really predicting the underlying data generating process too well. And again, that data generating process being this target function, the DGP. And the solution to this problem, at least one solution that we're going to talk about today, is known as regularization. And the idea behind regularization is that we are going to essentially tie our hands and we are going to restrain ourselves. We're going to restrain the complexity of our hypothesis set, of the set of functions we're thinking about using to choose our best fitting model. Okay, and I'm going to revisit this example where we started off with a blue target function, right? The blue function again here was our data generating process. A blue function was our data generating process. Red function here was our unrestrained model. Okay, by unrestrained, I mean we were free to make that as complex as we wanted. We chose a fourth order target here to perfectly fit that, or a fourth order fit model to perfectly fit that data. But we saw earlier that this does a terrible job of actually predicting the DGP. Rather, what we want to be able to do is restrain ourselves so we don't go all the way to a fourth order polynomial. We don't go too complex, but we maybe stop a little earlier in a way where now when we look at the target function, again, the DGP in blue here, and we compare that to our restrained model in red, we can see here that the restrained model in the right case does a much better job of actually predicting the DGP. The restrained model is doing a much better job of predicting the underlying data generating process. Okay, so that's really the idea behind regularization, is we're going to do something, okay, and this winds up us actually changing the optimization problem a little bit with respect to our cost minimization procedure. We're going to incorporate another term that forces a trade-off with respect to the parameters we're going to estimate. And this trade-off is going to end with the result of us not choosing a model that is as complex as what we would have chosen without restraining that fit. So again, the problem here was tendency is to overcomplicate the model, and we want to put on the brakes. So we're going to use a technique that'll kind of tie our hands automatically and help us put on the brakes and restrain ourselves. Now, how much restraining do we need to do? Okay, we're going to use another procedure called validation in a later segment to talk about exactly what's the right amount of restraint to use, but this is the general idea. So I want to go back to a familiar picture that we looked at in the last segment. That was us, and I think we had just started with it in this segment, but we were looking at this experiment where what we had done was we looked at this data generating process. We didn't have any noise in this experiment, but we would pick two data points, maybe here and here are two different data points. We would sample them, and then we would use those two data points to build our best linear hypotheses, which was a straight line going right through those data points. And then we repeated that experiment many times. And what you're seeing in the gray in the left diagram, that's the shadow of all the different hypotheses that we've generated from sampling just that finite sample, those two data points from that sine function. And we had started that experiment without regularization. We didn't restrain at all what the values of B0, beta 0, and beta 1 could have been in the regression model to fit those points. But it turns out when you use regularization, okay, what this winds up doing is it compresses the values of your beta parameters. Specifically in the regression case, it's going to compress those betas. And if the betas are compressed, if the magnitudes can't be as large, that means the lines that you can draw to fit the data, they can't be as wild. Okay, they can't have very crazy slopes, super high and low values for the intercepts. They're going to be restrained. And when you do this with regularization, okay, you'll notice it looks like that the fit of the all those different hypotheses in that right diagram here looks like a little bit better compared to the underlying data generating process in blue. Okay, so we saw before here that without regularization, our bias using the best linear function with both an intercept and a slope term was up at 2.1. We had a variance of 1.69. But it turns out when you use regularization here, we wind up getting a much lower out of sample error. Okay, recall here in the left diagram that our out of sample error was equal to 1.9. Okay, but over in the right diagram using regularization, our out of sample error is a lot lower. It is down to I got here 0.56. Okay, so in terms of predictive performance, okay, out of sample, the right model is doing better, okay, with respect to sampling error, right? Every data point that you could potentially sample, those change. Those are a random function of how you sampled from that population. Note here that between the left model and the right model, we did give up a little bit of bias. We gave up 0.002 bias, but that allowed us to gain the benefit of a tremendous amount of reduction in variance applying regularization and restraining that model fit, compressing those betas, not allowing them to be any value they want, but restricting them a little bit. Okay, so question is, at this point, how do we apply this technique? It looks like it's working. It is reducing our out-of-sample error here. So how do we apply this technique? Well, we're going to go back to this idea that every model that we're calibrating is really rooted in some form of an optimization problem. So this should not be a new idea at this point. But recall that we had some objective function, and this objective function, this cost function, was typically specified as our in-sample error. Okay, and our problem here was, well, we had to choose our beta vector to minimize the cost function, which was measured by our in-sample error, either using the sum of squared errors, right, the sum of squared residuals, the mean squared error, the root mean squared error. There was some cost function metric we had that we were trying to minimize by choosing these beta parameters. And what we are going to do to implement regularization is we are going to force a trade-off in this problem by adding another term. And this term we're going to add here, okay, is going to force a trade-off between the in-sample fit and really the out-of-sample error. Okay, so what we're going to do here is we're going to add a penalty term that's going to help us restrict the hypothesis set and really force this trade-off between the in-sample and the out-of-sample errors. Okay, and essentially really a trade-off between the in-sample error and the model complexity, the range of parameters, by using something called an augmented cost function, which is a cost function with a little something special added to it, as we had mentioned earlier. And what we are going to add to this augmented cost function is a specific term that we're going to call a penalty term. And we have a slight adjustment to that penalty term here. You'll notice we have this lambda over n out in front of that penalty term. And that lambda over n makes the calculus a little bit cleaner when you look at the solution. Doesn't really change the results of the parameter estimates since we're just really scaling by some constant here, but we're going to see that lambda is an important number to think about in this problem. Okay, this value lambda, okay, if that is 0, okay, that's going to be a value that we're going to choose as a practitioner. If lambda is 0, okay, then you'll notice the augmented cost function, C tilde here, that is the same as the original cost function up here. Those are the same thing if lambda equals 0. So lambda is a trade-off parameter. The closer it is to 0, the less of a trade-off we are forcing. Okay? As lambda is closer to 0, the less of a trade-off we are forcing. But the bigger lambda is, the larger this term in green over here becomes, right? The larger lambda is, the bigger this term becomes, right? And the larger the penalty will be. And we're going to see here the penalty is going to be an increasing function of the magnitude of the betas. So if lambda gets bigger, okay, it's going to make that penalty function get larger. And in solving the minimization problem, when we're minimizing this augmented cost function, the computer is going to worry now about, oh, well, I better make that penalty term smaller. And the only way for the computer to do this is to compress the betas. Okay, is to make the betas smaller to reduce that penalty. And when that happens, you will see really two things occur simultaneously. When we make the betas smaller, when we reduce the model complexity by trying to reduce this penalty term, okay, it's going to make this second term smaller, but lower complexity is going to start to drive our in-sample error up. And we're okay with doing that as long as the end result is we wind up with an overall lower out-of-sample error. Okay, so that so next question is, well, what is the form of that penalty function? And there are many different forms you can use, but one penalty function that is very commonly used in a technique known as the ridge regression is by taking the sum of the squared betas as the penalty, which is really that beta vector dot product with itself, beta transpose times beta, if beta is a column vector here. Okay, so that's what we're looking at, right? This is our penalty term. Okay, what does that dot product look like? Well, it is us squaring the betas and then adding them all up. Okay, so the bigger the betas are in magnitude, whether it's positive magnitude or negative magnitude, it's going to make beta squared and the sum get larger. That causes that penalty term to grow. And if that penalty term is there in that optimization problem, that means the computer is going to be concerned now, not with just minimizing the in-sample fit, but it's going to be concerned with minimizing that penalty. So I want you to think about this penalty term here. And we're going to talk about this more in the next segment. But this penalty term, okay, this is what we're really using to think about our generalization error, which is what we were calling omega. Okay, that was our generalization error. That is what that penalty term is trying to do. It's trying to proxy that generalization error, which we know at some point gets much larger with more model complexity. Okay, so what we're doing here is we're forcing a trade-off between the in-sample error, En, okay, and omega, right, our estimate rather of omega. If you want to put a hat above it here, that's fine. Call it omega hat, our estimated generalization error that we're modeling by using this penalty term in the regression. Now, what does all of this mean for our estimation technique? Well, recall in earlier segments, we showed that one way you recover these beta parameters is by actually solving that calculus problem, right? We wrote some pretty complex matrix calculus out. We solve for that pseudo-inverse estimator by taking the first order condition of that optimization problem, of this cost minimization problem up here. Okay, and now we're going to do it instead with the augmented cost function. We're going to put that up here instead of our regular cost function. And once we do that, it changes the calculus a little bit. And the form of our pseudo-inverse estimator in the case of this ridge regression is going to change form slightly from the pseudo-inverse estimator we had derived for an unrestricted linear regression. So let me again just show you how this fitting works, or rather this restriction on fitting works. Okay, so here are 4 different diagrams where we have exactly that same blue target function. Right, we got the same blue target function, and we're trying to fit it with our red function here. So in all these diagrams, again, that blue function is the data generating process. Okay, blue function is the DGP. Okay, red function in every diagram here is our model. And you'll notice as we move from left to right, hey, across these diagrams, what is happening? Well, as we move from left to right, hey, it looks like we are restraining the hypothesis more and more and more. Okay, in the far left case, we used a lambda value equal to 0. Okay, and if lambda was 0, then what happens to our penalty term here in the optimization problem? Well, that's 0. And if that is 0, the computer is trying to essentially just minimize the in-sample error in order to choose the beta parameters. And that results in overfitting. Okay, we're just trying to minimize that in-sample. We're fitting the data well in-sample, but we're not doing a good job out of sample. You'll note that as we start to increase that regularization parameter lambda, okay, once lambda is larger than 0, then this penalty term circled in green here, okay, in the optimization problem, this penalty term winds up becoming significant, and the computer now has to worry about, in solving this minimization problem, minimizing this entire quantity, the augmented cost function, it's going to have to think about shrinking the penalty term potentially at the expense of the in-sample error. So it looks like with the lambda parameter of 0.0001, we're getting a pretty reasonable prediction with respect to our model being an accurate representation of the underlying data generating process. Now, with any technique, it is possible you get overzealous, okay, and we can do what is known as overfitting the model. So if we increase lambda here by another factor of 100, okay, now you'll notice we start to kind of lose our fit, not only with the data, but we start to not even fit the underlying target function very well. And if we make lambda very, very large, Okay, if we make lambda very, very large, you'll notice now when we set lambda equal to a value of +1 in the far right diagram, now we're really underfitting. Okay, not just the data, but we're not predicting well on the data generating process. So it looks like in this picture here, or rather comparing these 4 pictures, there's maybe some optimal value of that lambda parameter. There's a right amount of brakes to put on, okay, to slow ourselves, to tie our hands with respect to model complexity. And that looks to be here, and we can't really know because I don't have the in-sample and out-of-sample error metrics shown here. But it looks like that second picture does the best job of actually predicting the data generating process with our model, despite the fact we are sacrificing a little bit of in-sample error to do so. Okay, so let's talk about some applications of regularization here. That's what this technique is called, right? Restricting our hypothesis set. Okay, generally referring to this technique as regularization by forcing this trade-off using the penalty term and then augmented cost function. And I mentioned before, when you do that, it changes the calculus associated with solving this problem here. It changes that calculus a little bit, right? What is EN? Well, EN is going to be some measure of in-sample fit, either, sum of squared residuals, mean square error, root mean square error, maybe integrated mean square, some error metric. Okay, and then we solve that optimization problem. We take the first order condition, we find a solution, and it turns out that we can still use a one-step learning analytical solution in the case of a ridge regression estimator where we're using that beta transpose beta penalty term. So at this point, it's a good idea to recall our pseudo inverse estimator when we were trying to really minimize the sum of square residuals. That was our non-penalized cost function from our linear regression framework. And that solution, when we solved that calculus problem, we took the first order conditions and we solved for our beta vector. What we found was the following. We could take the X matrix, which was our matrix of input data with a column of ones if we're including an intercept, and the solution to that involve this pseudo inverse matrix, which was X transpose X inverse times X transpose. And then we took that pseudo inverse matrix, we multiplied it by our output vector Y, and that allowed us to recover those beta parameters in one step. Okay, if we applied regularization and we added that penalty term, okay, we add that penalty term to this problem, meaning we are now minimizing not the original cost function, but we're minimizing this augmented cost function, which includes the penalty term. In the case of this ridge regression, we do also have an analytical solution that we can derive in a one-step learning fashion, very similar to how we derive the pseudo-inverse estimator. And there's a small adjustment here. Okay, and let me just talk about that for a moment. So here is the small adjustment. Okay, you'll notice that lambda variable, that parameter that describes how much regularization we're doing. The bigger lambda is, the more regularization we do, the closer lambda is to 0, the less restriction we're putting on our hypothesis set. That shows up here multiplied by this I matrix, which is known as an identity matrix. And the identity matrix is a matrix that has zeros along the diagonal. It's a square matrix. So from the top left down to the bottom right, you have all ones, sorry, not zeros. You have all ones across the diagonal from the top left to the bottom right. And then every other entry in that I matrix is 0. Okay, and we talked about the I matrix in an earlier video. That's like the matrix analog of multiplying by 1. If you take any matrix, you multiply it by the identity matrix, you will get back the original matrix value. So it's a very small adjustment here to implement regularization in the context of linear regression by utilizing this ridge regression estimation technique, which is predicated using really the same approach as we had to derive that pseudo-inverse estimator. So there is some calculus there. You can go through it if you'd like, but the end result of that calculus is this particular analytical solution. So if you wanted to find what are the betas when I implement some regularization in regression, all you need to do is change your pseudo-inverse matrix a little bit by adding this lambda I term inside the parentheses before you take the inverse. Okay, and that will give you the ridge estimator. So the pseudo-inverse matrix corresponding to this is just this orange portion, or the portion highlighted in red here. That is the new pseudo-inverse matrix, but incorporating that regularization parameter lambda. Okay, so it should be pretty easy to implement in R in your statistical software package if you can write out the regression in vectorized form and matrix form, and you can compute the pseudo-inverse. Now, there's a lot of other applications of regularization in regression. Okay, we looked at the ridge regression estimator, and the ridge regression estimator, again, what this does here is it shrinks our betas. Okay, by scaling them all down multiplicatively. It shrinks them by scaling them down multiplicatively, right? Our penalty term was beta transpose beta, and it's going to scale them down multiplicatively, meaning it's like we're multiplying them by some factor that is smaller than 1, right? And anytime you do that, it shrinks the variable's value down. But it does not scale any parameters down to 0. And that's important in the following regard. Okay, if we were to run regularization and we saw that, hey, it tells us one of the betas is 0, think about what that means. If any beta is 0, that's telling us we do not have a significant effect of that variable anymore, and that variable does not need to be included in our model. That's not going to happen when you apply the ridge technique here. The ridge technique does not result in model selection in this regard. Okay, it's not going to tell us which variables are important and which are not when we restrain the hypothesis set. It'll shrink the betas, it'll make them smaller, but it will not set any of them to 0. Fortunately, there is another technique known as lasso. This is another acronym here, but the lasso regression does both parameter shrinkage as well as model selection. Okay, and it does this by using a slightly different penalty term. Okay, it uses really an absolute value penalty term here, and it's an additive scaling. Okay, and when you're adding some negative number to scale something down, it's possible the negative number you add is big enough to shrink the whole thing actually down to 0. So if you use lasso, you may actually wind up in restricting your hypothesis set. You may wind up finding beta estimates that are actually 0 from this process, which will tell you not to include certain regressors or certain inputs in your model here. The problem with lasso is it does not perform well if you have highly correlated features. If you have issues like multicollinearity in your data, or you have very highly correlated inputs, it doesn't perform great. Ridge does a little bit better in that particular instance, but lasso has the benefit here of doing not only parameter shrinkage, but also variable selection, right? Ridge does not result in variable selection here. So when I'm saying model selection, what I mean is it's really telling us which variables to include and which to not include. Lasso does that, Ridge does not. There's another method known as the elastic net, which actually linearly combines the models of Ridge and lasso. Okay, so it kind of gives you a little bit of flavor of both there. There's another model, not as popular, known as the non-negative Eout method, which actually requires the OLS estimators as input. So there's kind of another layer of estimation you need there. A couple stages, you need OLS first. There aren't really popular R implementations as far as I'm aware of, but that tends to change over time as the nature of open source packages and their availability changes. But unlike lasso, the NNG performs pretty well if you do have highly correlated features. So that kind of wraps up our discussion of regularization, our restriction on our hypothesis set. We're going to talk about validation in the next series. Regularization, again, was a method for us to restrict the search through the hypothesis set. We kind of tied our hands, put on the brakes. Okay, but the problem was we didn't really know how much to put on the brakes. We didn't know how much to restrict ourselves, right? We looked at that one diagram where we had 4 different pictures and we had changed that lambda parameter, and we saw it was possible that we could restrict ourselves too much to the point where we're not curing overfitting, but we're causing another problem called underfitting. So validation is going to help us answer this question: how much restriction do we actually need to apply? Okay, when do I put on the brakes? And this is a very useful technique when it comes to fine-tuning model parameters. This is actually the technique we're going to use to estimate our out-of-sample error function. So validation is going to really help us estimate the out-of-sample error function here in a way that helps us put on the brakes, okay, so we do not get too crazy and make the model too complex. Validation is going to help us essentially answer the question of how much regularization do we need to slow ourselves down and to stop when we think our out-of-sample error is actually minimized at the correct level of complexity. So we'll pick up with that in the next segment on training and testing. Hope that was fruitful, and we'll see you soon.